Okay, any questions before we get started today? We're going to talk about disubstituted cyclohexane rings. Anybody have questions? So last time we talked about monosubstituted cyclohexane rings. And we saw that we have this chart here. This is not something that you need to memorize. I would give you these numbers, but we know that the larger this number here, the more we favor the substituent in the equatorial position. So this is equatorial over axial. And so certainly when we have a terp-butyl group, extremely highly favored for that terp-butyl group to be in the equatorial position. And essentially, when you have a terp-butyl group bonded to a cyclohexane ring, it essentially stays in the equatorial position. It doesn't even flip, okay, because it's so large. All right, so now we want to move on to talk about disubstituted cyclohexane. So cis and trans isomers. We know that for cyclohexane with a single substituent, we prefer the equatorial position. When we have more than one, we might not be able to get every substituent in the equatorial position. And so if that's the case, we want to make sure that the biggest group is equatorial. Sometimes we can get them both at equatorial, but not always. So we want to make sure that we can get the biggest groups in the equatorial position. So let's look at 1-chloro-2-methyl cyclohexane. And we have what we call cis and trans. So this one is trans. And that just means that the groups are on the opposite side of the ring. So this one's trans, and this one is what we call cis. We're going to use that terminology all year long. And that means that the groups are on the same side of the ring. In this particular case, we have them drawn where they're wedged, but you could also have them dashed, just as long as they're on the same side. So one up, one down, that means trans. Both down or both up, that means cis. All right, so these are completely different compounds because they can't rotate or anything. This can't rotate because it's restricted by the ring. So we can't convert a trans into a cis. Those are completely different compounds with completely different physical properties. So let's convert these to chair conformations. So that means we have to learn how to draw chair conformations. I'm going to have a handout posted. I don't know if it's already posted, but I'm going to have one posted if it's not already to the practice link that shows you how to draw chairs. There's a couple different ways of doing it. That's a very useful handout. We're going to just draw it today a little bit differently. It's nice to have more than one way to do it. We're going to do both chairs. One is going to be tilted slightly up, and one is going to be tilted slightly down. And if you draw it that way, it's going to make it easy for you to draw in axial and equatorial substituents. And we need to be able to draw both because when we do a chair flip, we get one way, and then we flip, we go the other way. And I think what you're going to find, like I find, is that one of them is easier for me to draw. And you'll probably have the same thing depending on whether you're right or left-handed. One of them is easier to draw. And so, so what I'm going to do is I'm going to draw two parallel lines, and so are you, tilted a little bit up. If you don't make them parallel with the edge of the paper, or you're going to have trouble when you're putting substituents in on the middle carbons. So I'm going to do like that. And then for the other ring, I'm going to tilt them the opposite way. So two parallel lines like that. And then if this is going down, if this is going up, I'm going to have a little V going down, connecting the two ends. So if the lines are slightly tilting up, the V is going to go down. And if the lines are going down, the V is going to be up. So I'm going to have a V connecting this end like that. So that's one chair. And then I'm going to do the same thing with the other. This is going slightly up, so I'm going to have this go down. And then this is going down, those parallel lines are going down, so I'm going to have a V connecting them going up. And that one, the right-handed one, the one that's on the right is easier for me to draw, okay? Now, we're not going to always have to draw in all of the bonds on every single carbon, but let's do it right now so we know how to draw them. Okay, and then when we draw these for real on the test, you only have to draw the bonds on the actual carbons that have substituents attached. But let's do this first. So if the V is pointing up, the axial is also going up, and it's going to be parallel with the edge of your paper. So it's going to alternate. We're going to go up. This V is pointing down, so this is axial is going to go down. This V is pointing down, axial is going to go down. I'll do the ones in the middle last. Those are usually the hardest ones to draw. And then on this here, this is pointing up, so the axial is going up. The middle carbons, again, are the tricky ones. And when you see them drawn professionally, like in your book and everything, they'll draw them the full length, and they will break the line either before or after. If you want, you can just draw them shorter so that you can fit them in. Because this isn't a textbook, this is our notes, and I will certainly let you do that on your test also. Because depending on how well you draw the chair, and that's for me too, sometimes I don't draw it, I draw it a little off, it's hard to fit those groups in. And let's do the same thing over here. So if the point is up, the axial is up, and it needs to be parallel with the edge of the paper. So this is down, and it alternates up, down, as you go around. It alternates up, down, up, down. Now, if you draw these axials on the wrong carbon, so for example, if on this first one here, if you drew the axial going straight up here, that would be wrong. You would get the whole problem wrong. So if it's pointing down, axial's down. If it's pointing up, then axial is up. And now the equatorials are a couple ways to look at this. The equatorial for this bond, if this axial's down, then the equatorial is slightly up. So a couple ways to think of the equatorial bonds. So that's my green. I'm just going to draw one of those for now so we can focus on here. One way to think about it is that if there was a mirror plane here, this bond is the reflection of that bond in a mirror. That's one way to think about this. The other thing, the way to think about it is see how this bond right here is parallel with this bond that's one carbon over. So that's parallel with that. So that's two ways to look at how the equatorial. The other way to think about it is if the axial's down, the equatorial's slightly up. It's not completely up. If you make your equatorials straight up and down like that, you would get the whole problem mark wrong. So that's a no partial credit thing. All right, so that means so this one here is the mirror reflection of that bond. It's also parallel to that one here. And likewise, we're going to go all around. The middle ones are a little bit tricky to draw, especially depending on how you draw your chairs. So just going to go like that. It's not really going to be the reflection of this one here, but I'm going to try to make it look parallel to that one. And likewise, this one here, the middle ones are harder to draw. Yes?
Can you say it's just parallel to those side ones? The middle?
Right here? What's parallel to that?
For the center carbons, the equatorial, if they're parallel.
Yeah, they're parallel to these side ones here like that. That's another way to look at it. Yeah, so let's go ahead and do that on this one too. And then I want to say a couple things about that. So you also notice if you go around in a circle, you're alternating slightly down, slightly up. Slightly down, slightly up, slightly down, slightly up. A common mistake on drawing chairs is for students to have, especially on the center carbons, to have both lines going straight up and down, and that's impossible. Okay, so you got to make sure that you draw all the equatories tilted. And notice, you know, these guys, depending on how well you've drawn it, these guys are essentially parallel. These guys are essentially parallel. But again, in the middle here, it's a little bit difficult to draw those middle carbons. So I want to say a couple things here. Axial bonds point in the same direction as the point of the chair to which they're attached. Equatorial bonds are slightly up, and we already said that. You have to be careful here. Now, you don't need to draw, if we're just having one substituent, you don't need to draw all these bonds, right? So don't waste your time doing that on the test. You only have to draw them on the actual carbon that has substituents. That's point number one. Point number two, if you leave it like this, and these are all supposed to be hydrogens, you would get it marked wrong because this is skeletal. And if you leave it like that, that means there's a methyl there. So if you want to draw all these in, good for you, but put hydrogens there. Otherwise, you'll get that mark wrong. Because if you don't put hydrogens there, then that's going to be assumed that it is a methyl. So a couple important things there. All right, so let's try this. A real example here. We're going to try to convert the trans, 1-chloro-2-methyl cyclohexane to a chair conformation, and then we're going to do the cis after that. All right, now what I'm noticing here is that the way I have this drawn, this chlorine is up and this methyl is down. So when I draw my chair, that chlorine is going to be up and the methyl is going to be down when I draw my chair. It does not matter which way you tilt your first chair. We're going to tilt it whatever way we want, but then when you do the chair, we're going to do the chair flip, you got to make sure it's tilted the other way. So I'm just going to do it to match what I have here, but again, you don't need to start with this. And let me do it right, I'm going to do it down here. So we'll have here, here's our parallel lines. Slightly tilted up, here's our parallel lines. Slightly tilted down. Since this is going, this is pointing up, the V is going to go down. Since these parallel lines are pointing down, the V that connects the two ends is coming up. That one is so much harder for me to draw. It is. And then the same thing here. This is pointing up, so the V is going to go slightly down. And this is pointing down, so the V that connects the two is pointing up. So there's my two chairs. And now when I put this chlorine up and I put the methyl down, I can start on any carbon that I want to. I usually try to avoid the two middle carbons, though, if I can help it, just because they're harder to draw. So I usually start on this right-hand side, but if you're left-handed, you probably are going to want to start over here. It's perfectly fine. But what we want to make sure that we do is that if we're tracing our substituents in the flat structure, I'm going to start with the chlorine, and then I'm going to go to the methyl clockwise. We have to stay clockwise on the ring. That's going to make more sense in Chapter 5, because if you change the orientation of the relative orientation of the groups, you're making the enantiomer. That doesn't mean anything to you right now, but it will next week. That will mean something to you. Okay, so I'm going to do it on the right-hand side because that's just my habit. I'm going to put the chlorine up. So the axial is up on this bond. Equatorial is slightly down. And I'll put the hydrogen there. Now, hydrogen is understood, right? I don't have to put that hydrogen. I could leave this hydrogen off. And if you're really confident that your chair, that anybody who looked at your chair, including me or any of the graders, knows that that bond is axial, then you don't have to put the hydrogen in. It's helpful to put the hydrogen in because if you don't draw really nice chairs, it makes everything clear, okay? You do have to know how to draw things axial. I have some students who'll just write a line like that and a line like that, and they'll just label it axial and equatorial. No, you have to actually draw it axial and equatorial. So that to me makes that really clear, so I'm putting that hydrogen in. So that's here, that's carbon 1, and I'm not numbering to name this compound, I'm just numbering to trace the substituents. So that's carbon number 1, and so I'm going clockwise, and so I want carbon number 2 to be right here. That's going to be carbon 2. So I'm going to draw my 2 lines, my equatorial and my axial. The methyl is down, so that means it's on this carbon. Just like that. So this chlorine here is up above the hydrogen that's on the same carbon. That's up, that matches that. This methyl is down below the hydrogen that's on the same carbon, up, down, and there are trans that are on opposite sides of the ring. Questions on how I did that? Now comes the fun part, the chair flip. Okay? So we're going to keep track of the headrest and the footrest. Here's the headrest. Here's the footrest. I'm going to be moving this down, and I'm going to be moving this up. The models that you have, if you have the green box, those are really good for chairs. So he has one right here. Can you hold that up? That's really good for chairs. I have the more expensive models. They're not as good for chairs as those guys. The more expensive models are too flexible, so they're not as good for chair flips. Those are actually excellent for chair flips. So that means that this carbon right here is going to be here, and this carbon right here is going to be here. So on carbon number 2, I did a chair flip, so that means the methyl is going to be equatorial. Notice it's still going to be down, but now it's equatorial. I'm going to keep track here. That's carbon number 2. Common mistake at this point. I've done this. The footrest is now the headrest. Common mistake would be to put the chlorine right here. Is that right? Okay. If I put the chlorine right here, then I need to go clockwise. So number 1 has to be here, not here. See, 1, 2 clockwise. If I put the chlorine right here, then that would be 1, 2 counterclockwise. Don't want to change the direction. So that means I'm going to have to go over here onto this middle carbon, whether I like it or not. So let's draw the groups in. I'm just going to make it short. I think you guys have an easier time with that. Is the chlorine is axial in the first chair, so that means it has to be equatorial in the second chair. So this is this here, and this is that right there. It's not a C. Why did I do that? That's a Cl, not a CH. Okay. So that's number 1. And that's number 2, and I'm tracing around clockwise. Questions on how I did the chair flip? Yes?
Can you point out 2 points of the Cl on both? So is that one on the left the same one that you put it on?
It is. So let's mark. So remember, when you have a chair, you've got 4 atoms that are in the same plane. That's the chair part where the guy is sitting, right? So those 4 atoms are still in the same plane. And the chlorine is actually attached to the chair, where the guy sits, rather than the headrest or the footrest. So it stays there.
It's just that the actual equatorial.
It just looks different. More questions? That's probably the hardest thing to do with chairs. Yes? Excuse me? Yes, you certainly could have. Yes, you certainly could have. And some people actually like to put them on the middle carbons because then it doesn't look like they're flipping. It looks more like they're staying on the same carbon. You can certainly do it that way. Okay? Just make sure. If we're going clockwise here, we go clockwise here, we go clockwise here. All right, so now which one is going to be the more stable chair conformation?
First one on the right.
The one on the right, because they're both equatorial. The groups are equatorial. So this is diaxial, and this is diequatorial. And just to point out here, this chlorine is still up, this methyl is still down. And when we're looking at up and down on the chair, we mean this chlorine is up above the ring, it's up above the hydrogen, which is on the other side of the ring, and this is down below the ring, below the hydrogen, which is on the other side. And then this is diequatorial, so this is still up above the plane of the ring, and this methyl is still down. This, of course, is the more stable conformer. And it predominates in an equilibrium mixture at room temperature. So we're going to have long arrow to the right, short arrow to the left here for our equilibrium. Excuse me?
What's the last word?
Room temperature, RT. All right, now let's do the same thing with the cis. We had so much fun drawing that first chair, those two chairs, and we're going to draw some more, okay? So again, chlorine's up, methyl's up this time. They're both up. So that's cis. Let's draw our two chairs. I'm going to tilt them the same way I did this guy here. And you got to get the right tilt. Too much, and you're going to have problems when you're trying to put substituents on. So this one's pointing slightly up. We're going to have a V connecting the two ends going slightly down. And I'm just going to start on this end again. I'm going to use these two carbons. So let me just draw my axial. This point on the chair goes up. The axial goes up. Here's my equatorial. And then I'm just going to fill in the groups. And I don't need to draw hydrogens in, but I'm going to. I like to draw them on the carbons that have substituents. Okay? By the way, I want to point something out here I just thought of. This is a perfectly acceptable way to draw this compound with the chlorine wedged and the methyl wedged and leaving the hydrogens off. It's understood that the hydrogen is going back, right? We all understand that? You cannot draw it that way in sapling. You cannot draw it that way in sapling. Sapling's a computer. And if you have any wedges on a carbon, you have to draw in all of the hydrogens. So in other words, if this was on sapling, I would have to do this. You have to draw that on sapling. What happens if you don't draw those in? Sapling, the computer, makes a 50-50 guess on whether you have it right or not. So you could be drawing it wrong, you won't know. You could be drawing it right, you think you did it right, and you actually did it wrong because it makes a 50-50 guess. It's a really hard thing to remember, but you have to, anytime you have a stereocenter, we don't know what stereocenter means. Anytime you draw dashes and wedges on an atom, you need to make sure you draw the hydrogens in, okay? So that's just a little thing you're going to already run into in Chapter 4, and even more so in Chapter 5. Okay, so we're going to put these on the end here. So this chlorine is up, so I'm going to put this up. Hydrogen down. Please make sure you put that hydrogen in. If you don't, it's a methyl. This methyl is up. That hydrogen's down. I am tracing this around clockwise. So this is carbon 1, carbon 2, carbon 1, carbon 2. And then I'm going to keep track of the headrest and the footrest here. This is the headrest. That's going here. It's going to be now the footrest. This is the footrest. There's the headrest right there. So the headrest is carbon number 2. So that means carbon number 1 will be right here because we're clockwise, clockwise, clockwise. It looks like we've moved the groups over, but we really haven't. If we focus on this being the seat, that's still the seat right here. All right, so I'm going to draw my bonds in here, and then I'll fill in the groups. Axials down, equatorial slanted as much as you possibly can. So I'm going to look at this carbon first. That methyl here is equatorial. That means it's axial. And then I'm going to double check to make sure I haven't made a mistake. It's still up. It should still be up. So this is up. It should be up here still. The chlorine is on carbon number 1. It's axial here. It's equatorial here. And then the hydrogen, again, sometimes just easier to draw it. Just that bond a little smaller. I think it's easier for you. So which one is favored now? By that chart, axial energy, methyl has a larger axial energy than chlorine. It's actually bigger. Now, it might be different van der Waals radii. Van der Waals radii give us an idea of the size, right? But remember, it's the size, and it's the size, and it's how close it is. So it also has to account for bond length. So although chlorine, I don't know what the van der Waals radius, we could look that up, and we could look this up. But this bond is a lot longer, so there's not as much of an effect. So we want this one to be equatorial preferentially. So long arrow to the left, short arrow to the right. So question, which one is favored? And the answer is methyl has a larger axial energy.
So you want that one that with a larger axial energy always to be in the equatorial position?
That's correct. Everybody hear what he said? The one with the larger axial energy gets at the equatorial position. Axial energy than Cl. So the conformer on the left, you can call it a conformer, you can call it a conformation. If you want to sound really pro, you'll call it a conformer. The conformer on the left. Doesn't that sound more professional, I guess? At the left is favored. All right, questions? Anybody? So the same definition of cis and trans can be applied to other substituents on other positions on a cyclohexane ring. So again, we had so much fun, we're going to do that all the way over again, but we're going to go a little faster this time because you're getting good now. I'm going to tilt this. I'm going to go, and it doesn't matter here which way. I'm going to tilt this one this way, and I'm going to tilt this one this way. See, so now I've done the one that's easier for me to draw first. It does not matter. And these rings where the substituents are in the 1,4 position seem to be the easiest to draw. 1, 2, 3, 4. So I'm going to use the headrest and the footrest position. So I'm going to draw my bonds, and then I will fill them in. So likewise over here. So methyl up. So then the methyl goes right here, up above the hydrogen that's on the same carbon. And if we trace that around clockwise, 1, 2, 3, 4, we're to this carbon here. This is also up, so methyl is up here. So notice one is axial and one is equatorial. And of course, when you do the chair flip, it's going to be the same, except they're going to switch places, right? So here we have headrest, footrest. So now the footrest becomes the headrest becomes the footrest. And so on the right-hand side, the methyl was axial before, it's now equatorial. It's still up. That's good. That's what we want. That's carbon number 1, 2, 3, 4 over here on carbon 4. This carbon here, this methyl is equatorial. It's now axial. It is still up. And you want to just check yourself the whole way. Those two chairs are exactly equal in energy. So I'm having equal arrows. So each has one axial and one equatorial. And since the groups are the same, they're identical in energy. All right, so that's disubstituted cyclohexane. Let's talk about disubstituted cyclopentanes. And cyclopentanes are not in a chair, right? So we don't have to draw chairs. They're a lot easier to draw. We're just going to draw them flat. All right, so let's look at 1,2-dimethylcyclopentane. Which one is this, cis or trans? This is cis. This is cis. This is trans. Two ways to draw. This way here, where the ring of the plane is in the paper. And we've left the hydrogens off, but they're there. So hydrogens are what we call understood. That means every chemist knows they're there. Understood, except by sapling. Okay, sapling doesn't understand. All right, so that's the deal. Is you want to know you don't want to get your problem marked wrong if it's correct, and you don't want to think that it's right if you're doing it wrong. So that's why we want to make sure we do it that way. Another way to draw this is to have the actual ring perpendicular to the page. So you kind of draw it a little bit flattened, and then this part is wedged. So that the ring is kind of floating above your page, perpendicular to your page. And if it's doing that, then we draw the groups going straight up and down. So I know you're probably going to not want to draw it this way, but you will see it drawn this way. You will see this drawn this way in chemistry textbooks, and you will see it drawn that way in OChem textbooks. And technically this line should go up higher, but we're just going to draw it short so we can fit it in there so we don't have to worry about crisscrossing those lines. Because remember, when we crisscross lines, if we don't break the one that's in the back, that's a new bond between, that's a new bond that we're making that shouldn't be there. So that one is like that, or for this one here, we can draw it like that also. So methyl would be up here, this would be a hydrogen, and then down here's the hydrogen, and here's the methyl. So that's two ways of conveying the same information. So again, the ring is perpendicular to the plane of the paper. All right. Let's talk about oxidation of alkanes. Don't really know why that's in this chapter because we really talk about oxidation of alkanes in chapter 15, but this is where it's placed in this textbook, so that's where we're going to talk about it. So alkanes are extremely unreactive. Stable, low-energy species derived from petroleum and petroleum byproducts. So we take petroleum and we distill it. So this is what we call a fractionating column. So we do a distillation with using a fractionating column. So we have our crude oil. It gets heated in a furnace. And then we're going to separate the different components of the crude oil in this fractionating column. Notice that the temperature goes lower as you go up. And then we collect these different fractions. So if we collect fractions from about 3 to 4, that's liquefied under pressure. So that would be where we get our propane tanks for the grills. That's where you get the cigarette lighters. That's where you get the propane in the cigarette lighters. That's 3 to 4 carbons. I left the carbons off there. 3 to 4 carbons. Gasoline is about 7 to 11. Do not need to memorize these carbon numbers. After it's freshly distilled, it's not very good, so they do catalytic cracking to improve the gasoline. Catalytically cracked to improve the quality. So 7 to 11 carbons, and we know for gasoline, the 8 carbon is the best, high octane gas, right? So they do this process to improve the quality. And then you have kerosene, which is about 12 to 15 carbons. You'll find a big range when you look for the number of carbons online, I noticed last night. So these are approximate ranges. Diesel oil is 11 to 18 carbons. Fuel oil is 20 to 27 carbons. And then when you keep going here, you actually get to higher temperatures, and you actually have to use a vacuum. We get lubricating oil, paraffin wax, and really pretty much what's left over is asphalt. So we use all the parts of the crude oil. And of course, we are quite dependent on it for heating our houses and putting in our cars so we can get around, right? Okay, so there's only 2 reactions that alkanes will undergo. They're incredibly stable. Both of the reactions that they do undergo are free radical reactions. And we're going to talk about free radical reactions in chapter 15. So we'll come back to this in chapter 15. So this is sort of a little intro. Reaction 1 is combustion. Of course, we know that's what we use, why we use gasoline in our cars, internal combustion engines. So here's methane. And if we do combustion of methane, we get CO2 plus 2 H2O. That would be complete combustion. That releases a lot of energy. Delta H naught is minus 210.8 kcals per mole. But we also, of course, don't get complete combustion all the time. We get incomplete combustion. Incomplete combustion gives us carbon monoxide, and carbon. So incomplete combustion. So we certainly get carbon monoxide out of the back of our cars and carbon. And the second reaction is halogenation. Again, this is chapter 15, so we're not memorizing this. This is just sort of a little, okay, we're going to be talking about this in the future. High temperature or light. And for light, I'm using H nu. So high temperature or light, we can halogenate 80%, 10%, and small amounts of these others. This again is chapter 15, not something that we're going to worry about right now. Both of these reactions are oxidation reduction reactions, and we are going to talk about oxidation reduction reactions in chapter 12. So that's not till 51B. So all of this stuff we're not going to worry about too much right now. So you know from Chem that an oxidation reduction reaction involves oxidation is loss of electrons, reduction is gain of electrons. So here's a Chem example for you. We have copper going to copper 2+, so it's losing electrons, right? Loses 2 electrons. The silver, on the other hand, we have 2 of them. Each one of them is gaining an electron to become silver crystals, so that's gains electrons. Therefore reduced. So if one molecule is oxidized, the other, another is reduced, and electrons are transferred completely. Electrons are transferred from the copper to the silver, complete transfer of electrons. Different in organic chemistry. Oxidation, it involves loss of electron density. We're not actually transferring electrons completely because most of the compounds that we have don't become are ionic compounds like that. So we don't transfer electrons completely, we transfer electron flow, changes to the opposite direction. So for example, here we have loss of carbon hydrogen. So this is what we're going to look for to know whether something's been oxidized or reduced. Loss of carbon hydrogen and gain of carbon X. At the same time, both things have to happen. So carbon, of course, 2.5 electronegativity, hydrogen 2.2. And we still have carbon 2.5 here. And X is going to be greater than 2.5. So X could be oxygen, nitrogen, halogens. Those would be the ones that most obvious examples that come to mind. So oxygen at 3.5, nitrogen 3.0. So if we look at the way the electrons are flowing, when we have a carbon-hydrogen bond, their electron density is actually flowing towards carbon, right? Because it's more electronegative. When we now replace that hydrogen with an X, electron density is flowing the opposite direction. We haven't transferred electrons completely, but we're changing the electron flow. Reduction is the opposite. Carbon gains electrons by giving up bonds to more electronegative elements and forming bonds with hydrogen atoms instead. So we have to have both of these things happening. Loss of carbon X, gain of carbon hydrogen. That's a reduction. Again, X equals oxygen, nitrogen, halogens, etc. Anything that's more electronegative. So here we have electrons flowing towards X, and now we have it flowing towards carbon. So we've changed the flow of electron, the direction of the flow of electron. So here's some examples where we're going all the way from methane all the way to carbon dioxide, so complete combustion of methane. And so let's look and see what this looks like. So what we've done is here we have carbon with 4 bonds. We've lost one of them, right? Any one of them we've lost, doesn't matter. I probably circled the one that's not obvious, but we've lost a carbon hydrogen. and gained a carbon oxygen. So we want to have both of those things. Loss of carbon hydrogen, gain of carbon oxygen. And let's follow this all the way across. Well, we won't follow this all the way across because it's 950, but you'll notice, you try to do this on your own. Every time we go to the right, we lose a hydrogen and gain a carbon oxygen. So we'll continue this next time.